Hi folks, Mr. Long here with a screencast where we're going to take a look at exponential, tables of values that can be represented by exponential functions. And first thing we're going to do is take a look at this table. So we've got our x and y are here in this table in these two columns. And my apologies for the number of decimal places, but you know how precise I am. I just wanted to make sure that we had everything right. No, actually, I just forgot to set the rounding feature in the spreadsheet. So what we need to do first, folks, is take a look at this table and see if we can make sense of it. So there's a few things that I would look at on the table. So first thing I'm looking at is it growth or decay? And I can see I go from 100, 113, 120, 128. So it looks to me like it's growing. Another thing I might do is take a look at these values and just make a really rough sketch. So if this is, again, money growing, so after 1 year I had $106. After 2 years I had $113, and so on. 3 years, $120.79. 100 years ago, theoretically, I had $20. So what that tells me, if I look back in the past 100 years, that's after doing so let's see, negative exponents means repeated division. So if I had repeated division 100 times, I would still have $20. So here's what that tells me, is that I've got, way back in the past, here at negative 100, I had $20. So for some reason I went along, $20, $20, and then it started to grow. Okay, so that means that this negative 100, the value there is 20, that means I've got a horizontal asymptote at y equals 20. Okay, that's right there at y equals 20. There's a horizontal asymptote. Okay, and that gives me my c value as well. So in the model. Oh, by the way, the whole point of this is to develop an equation in both forms, percentage growth form and doubling time form. Okay, so what I would do is I'm not going to do differences that include 106 years in the future or 100 years in the past. I need to do differences that are spaced by the same interval. So in this case, they're all spaced by 2, right, or by 1. So I'm going to do differences, and I always start at the bottom and work up. So the first difference I would do is 146.99 minus 137.57, and that gives me that answer. Then again, I do the subtraction there, subtraction there, subtraction there, and so on. And then these are my differences right here. So that's how much it's growing by. So we have growth here of each of these values. If you notice, it's not growing by the same amount each time. If it was growing by the same amount each time, what kind of relationship would it be? Maybe linear, right? But it's growing by an increasing amount, so it's a nonlinear relationship. And we're working on an exponential functions unit, so we're going to check and see if, in fact, it is exponential. The way we do that is to do ratios. So I do, the first ratio I would do would be 9.413 divided by 8.716. And that works out to 1.08. And I keep doing those same ratios, and I get the exact same ratio every time. With a constant ratio, I have exponential growth or decay. Since my number is bigger than 1, since this number here is bigger than 1, my ratio is bigger than 1, my repeated multiplier is bigger than 1. If I'm multiplying by a number bigger than 1, I have growth. Okay, so I'll write that down here. I've got a b value of 1.08. That's my repeated multiplier. But this table, we do have a problem in this table because it only has an x value of 1 and that y value. I don't have the y-intercept. Now, there's a bit of a problem in this, in that of this 106, normally I could, under normal circumstances, I could just take that 106.4 and divide by 1.08 to give me my y-intercept. But not all of that 106 is growing because I have a y-intercept of 20. In other words, I have $20 that's a constant. It didn't grow at all. It's not growing. So of that $106, only part of it has growth by 8%. Okay? So this is a more complex problem when the horizontal asymptote is not 0. So let's go to the next page and see how we might address it. So the only thing I know right now is the b value of 108. Oh, and I know the c value of 20, because I know that a long time ago in the past it was at 20. So let's go to the next slide. Okay, so what is A? That's what we want to figure out. What is that A value? And I know it's, what I can do is I can use this information. I've already figured out that B is 108. I know that C is 20. That's a horizontal asymptote. I've got lots of ordered pairs on the table. I picked this one. And the reason I picked that one is because this value was 146.999, I think, which rounds to 147 even. So that was the closest one, the nicest one to work with, 6,147. So now what I do is I can substitute that into the function and solve for A. So I've got a Y value that comes from my ordered pair, 147. I do not know the A value. The B value I know is 1.08. I'm looking at how much money there is after 6 years, and after 6 years there was the $147. So the exponent is 6, and then I have to add on my constant, which I know is 20. And now I have exactly one unknown A in one equation, so I can solve that. So to solve this, I minus 20 off both sides, and that will give me 127 equals A times 1.08 to the 6th. And then what I want to do is divide both sides by 1.08 to the exponent of 6. So A will equal 127 divided by 1.08 to the exponent of 6. So if I do that, I think I'm going to get a value of, and let's see, I should get a value of 80. Okay, the A value will be 80. So if I check that, whoops, sorry folks. So I'm going to write that in blue to see, so A then equals $80. So what does that mean? Well, I'm going to go to the next page to start to look at that. So that's an algebraic strategy to figure out A. So what does it mean? Well, I'm going to write, even though I have, I've got method 2 here, I'm going to start by writing in the bottom. Can you look just to the bottom of the screen? And our equation we know now is this. Y equals 80 times by 1.08 to the x plus 20. So if that's money, it means that there's $80 that grows at 8% per year, and then I've got $20 invested as well. It's not growing, so that's a very bad investment, right? So I have $80 that grows at 8%, and then I have $20 that does not grow. That's the horizontal asymptote. So altogether, how much money did I have at the start? Well, $80 times 1.08 to the exponent of 0 for the y-intercept. 1.8 to the exponent of 0 is 1. 80 times 1 is 80, plus that 20 is 100. Okay, so now I have to, let's forget that we have this answer right here, and let's look at a totally different strategy, what I call a recursive strategy, so we're looking back. So one of the things that we know is we figured out that because we have a horizontal asymptote that's not 0, it's actually 20, I know that of that, so I've already figured out that asymptote, that $20 is not growing. Of that, of all the amounts of money, there's $20 that doesn't grow, and it stays constant all the time, that $20. So when after 1 year, when I have $106.40, $20 does not grow. Well, how much of it does grow? Well, it's going to be 106.40 minus 20 equals 86.40. So $86 of that 106, $86 is growing and $20 is not growing. So if you remember yesterday, we took that $106, we would have taken that $106 and divided by 1.08 to go backwards in time by 1. But that's when all of this value was actually growing. So we don't have all this growing. We have $20 that's growing, and we have $20 that's not growing, and $86.40 that is growing. So now what I have to do is to take that 8640, and that, since that's the part that's growing, and I can divide that by 1.08, and then that in turn will equal $80. Okay. So at the start, I've got at 0 years, I've got $80 that does grow, plus that 20 that's not growing, for a total of 100. Okay. And what it does is the $80 is growing, which gives us our A value. And then we already knew the 20. There's our 20. And the 1.8 is 1.08%, or 1 plus 8%. So let's take a look at the next page and sort of summarize that. So y equals 80 times by 1.08 to the x plus 20. 80 times by 1 plus 8 over 100 to the x plus 20. So I've got $80 that grows at 8%, and I have $20 that is constant and does not grow. Okay, and that's what that means, that equation. Okay, so of our y value, I've got this $80 that's growing and the $20 that's not growing, that is constant. So it's a more complex relationship because of that horizontal asymptote. So folks, that is how you get that equation. The other piece is the doubling time equation, and I'm just looking at our table. This is you know what, I think today, with these types of equations, with doubling time, I think I'm going to leave it so that you just get the percent form. You know, if you want, you can certainly get the doubling time form. And I guess, how would you do that? Well, in order to get the doubling time, you've got to figure out how many times, so 1.08 to what exponent, how many years, will equal 2. Okay, and we've already done that. We took the log of both sides. So the log of 1.08 would be, what is the log of 1.08? The log, let's see, I'll put that in my calculator. So I'm going to take the log of both sides. The log of 1.08 is 0.033. So that's going to be 10 to the 0.033x equals, and then we do the log of 2. And the log of 2 is 0.301. I should have known that. 10 to the 0.301. And then to solve that, I just take, we've already done this in class, I take 0.301 and I divide it by 0.033. So it's, yeah, so take 0.301 divided by 0.033. Yeah, which is about 9.1. So that means our half-life is, x in this case is 9.1. So I've got it, yeah, and that's what it should work out to, is 9. So let's move that to the next page. So the final way I can write that is, with percent form, it's starting at 80 that grow, 1.08 to the x, plus 20 that doesn't grow, equals, starting at 80, doubling once every 9 years, or 9.1, plus $20 it does not grow. And that, folks, those are your equivalent representations. One in doubling time form and one in percent growth form with asymptotes. What you can do now is you'll be able to do number 2, number 4, number 6, and number 8 on the handout from yesterday. Okay, if you can work through those, the answers are on the bottom. And you treat exponential decay the same as exponential growth. Your equations just will, instead of having a 2, for example, it'll be a 1/2. And instead of 1 plus 0.08, it might be 1 minus 0.08, for example. Okay, so good luck in doing those. I really encourage you to go back and rewind and go through this Screencast again if you need to, and pause it wherever you need to, and you might even want to work through this specific example before you go ahead and do the worksheet questions. Have a great day.